Today is the introduction lecture of the course of Advanced Manufacturing Technologies. The content of our lecture is following. First of all, I will consider our course Geometric Modeling. I will briefly tell you about the content of lectures and practical tasks. Then I will present you the topics for your master's thesis provided by our research group. Our course contains two parts. The first one is geometric modeling, the second one is heterogeneous volume modeling. The course of geometric modeling is devoted to homogeneous forms, approaches, and algorithms for their definition, transformation, and visualization. The heterogeneous volume modeling course focuses on mathematical models for modeling 3D objects with different distribution of properties within an object, such as density, color, opacity, multi-material, and so on. Such models can be used in physical phenomena simulation, medical software, or 3D printing. Now I want to do a small introduction to these courses. Before starting, I'd like to introduce basic notions which we will often use in our lecture when we consider geometric forms or methods and algorithms for its definition. So, we will consider a shape as a point set in n-dimensional geometric space, for example in Euclidean space. The next notion is a unit cube. We will use this notion for parametric definition of shapes. A unit cube in k-dimensional space is a set of points with all coordinates changing between 0 to 1. Here we can see one-dimensional cube or a segment, two-dimensional cube or a square, and three-dimensional cube. We have to distinguish between the dimension of a space and the dimension of the shape embedded in this space. Roughly speaking, shape dimension is the number of coordinates needed to specify a point in the object. The following definition is more formal. A shape is k-dimensional if there is a continuous one-to-one mapping of the k-dimensional cube to this shape. This table shows the dimension of the shapes in geometric spaces. As we can see, dimension of shape can be equal or less than dimension of space. A point is zero-dimensional mathematical object which can be specified in any n-dimensional space using n coordinates. Curve is one-dimensional, surface is two-dimensional, and solid is three-dimensional shape. We will also consider a special type of objects called volume, which is three-dimensional object in four-dimensional space. Volume can be also called a hypersurface in four-dimensional space. How can one define such shapes? There are several basic ways to do this. The first one, making a list of all points of the point set. The second way is mapping of a known set. The third way is point membership rule, and finally the generation rule. The simplest way is to make a list of all points of the point set by providing their coordinates. Linear array defines one point in n-dimensional space. As example, a list of 2, 3, and 4-dimensional points are presented on this slide. It's obvious that only finite point sets can be defined in this way, and no continuous shape, such as curve or surface, can be defined. Lists of points became popular with introduction of 3D scanners generating point clouds in the object surface. These clouds serve as input data for object geometry reconstruction in different forms. By hand we can introduce only a short set of points. Now look please at this human brain and a squirrel scanned by a laser scanner. Of course it's also a finite list of points, but the number can be million points, which then help to increase the precision of the shape interpolation. A list of points became popular in animation with introduction of particle systems, which are a cloud of moving points with predefined behavior used to model fire, smoke, water, and other nature phenomena. These are examples of particle systems modeled as list of time-dependent points with some attributes assigned for rendering purposes. We will study particle systems in more detail in the next lectures. The next way for shape definition is mapping from a known set. If the set A is defined, Mapping M established one-to-one correspondence between the set A and the new set B, as you can see on this slide. Parametric curves, surfaces, and volumes presented later in this lecture are defined in this way. The first example of a mapping is a well-known expression, y equals some function of x. This expression defines a curve in two-dimensional space, but it uses a single parameter x, so the curve is a one-dimensional shape. If we add one more parameter, for example time, we can get an animation as you can see on this slide on the right side. The second example of a mapping is a function of two variables. It defines explicit two-dimensional surface in three-dimensional space. Other terms for such surface are relief surface, height field, or a depth field. If we add the time parameter, we can get an animation. There is an example of a mapping of a function of three variables. It defines an explicit hypersurface in four-dimensional space. Also, it's called volumetric object, voxel object, or a 3D scalar field. You can see an example of rendering such a 3D scalar field in the right image. In this case, the smoke density is the value of the function. Here you can see the frames of volumetric animation. It's rendering of time-dependent smoke density function. Now let's consider a 3D parametric curve. It's defined by mapping of one parameter u to the coordinates of our curve. This is a one-dimensional shape in three-dimensional space. In the same way, we add the time parameter and get an animation. A surface is a two-dimensional shape in space of any dimension. It means any surface patch has one-to-one mapping to a unit square. In the shown example, our known set A is a unit square. The new set B is a parametric surface. The mapping M is given by a set of parametric equations for each coordinates x, y, and z with the parameters u and v. By giving any arbitrary values from 0 to 1 to the parameters u and v, we substitute them to the parametric equations and calculate coordinates of the corresponding point of the surface. Thus, the entire square is mapped to the entire surface. This is an example of the parametric surface. Texture is used to show the mapping from the unit square. The grid on the surface is mapped grid of the unit square. A solid is a three-dimensional shape in space of any dimension. It means any solid has one-to-one mapping to a unit cube. Parametric solid can be defined by mapping of a unit cube onto the solid. As we can see, the mapping procedure is quite similar for 1, 2, and 3-dimensional spaces, with only difference in additional dimension. Now we switch to the next approach to defining a point set. It's a point membership rule. A rule may be established which allows for any given point to judge if it belongs to the newly defined set or not. Implicit curves and surfaces and functionally defined solids and volumes are introduced in this way. Implicit curves and surfaces are defined using continuous function of 2 or 3 point coordinates respectively. For example, a set of points with function f of two variables x and y is equal to 0 defines an implicit curve, which is a boundary between two other sets of points on a plane. Inside points with positive function values and outside points with negative function values, as you can see in the circle in figure. Solids are defined with the inequality. Solids have dimensionality equal to the space dimension. Solids are n-dimensional objects in n-dimensional space, as a two-dimensional disk in the two-dimensional space shown on this slide. Disk is a solid with internal and boundary points belonging to it. Let us make a step one dimension higher and consider functions of point coordinates in three-dimensional space. The equation f equals to 0 defines an implicit surface, and the inequality f greater than 0 defines a three-dimensional solid with the implicit surface as its boundary. Symmetrical to the two-dimensional case, the equation defines an implicit surface called a sphere, and the inequality defines the sphere and all the points inside, making an object called a solid ball, or simply a ball. Finally, we discuss a generation rule as the way to define a shape. A rule can be specified to generate a shape in a recursive manner, starting with some initial shape, usually very simple, and use the current shape as input at the next generation step. In this way, fractals, Lindenmayer system, and other procedural models can be defined. In the case of L systems, the shape generation starts from one or two simple shapes. This initial shape is assigned some symbol called axiom, and then some formal grammar is introduced by giving substitution rules for the involved symbols. For example, X can be small lowest segment of the tree, and F can be one leaf. Then the rules are applied iteratively to the current shape. The next topic of our lecture is transformations and deformations of the shape. Our course includes practical tasks where you can implement your own geometric kernel with basic transformation operation our shapes. Moreover, using such operations, we can create a simple animation. The first operation that we will discuss is a two-dimensional translation of a boundary represented shape. In this operation, we just translate the vertices and then redraw the lines between them. The translation operation preserves distances between vertices and angles between vectors. The next operation is rotation in two-dimensional space. Rotation is defined about the origin by the angle theta. The positive angle means counterclockwise rotation and is measured from the positive direction of the x-axis. The example shows that rotation about the origin changes coordinates of all points, including the lower left corner. The next operation is scaling. Note that scale operation does not preserve distances between points or angles between vectors. See the house increased in size and displaced after the scaling was applied. Now let's consider deformation operations. Twisting is a general form of rotation. You can think of it as a rotation about an axis with angle of rotation changing along this axis. It's reflected in the expression for angle theta equals function of z coordinate. Examples shows a cube and teapot twisted. Also, operation for forwarding mapping and inverse mapping, which are used in different shape representation, are represented on this slide. Tapering is a generalization of scaling where the scaling factor changes along some axis. We can see the examples where the scaling of the teapot and the cube change from the left to right. The scaling factor r is given as the function f of z coordinate. Bending is also kind of non-linear rotation with the axis usually orthogonal to the symmetry plane of the object and the angle of rotation changing between 0 and 180 degrees. At the lower right corner we see a composite transformation including tapering, twisting and bending applied consequently to a superellipsoid. The above operations change the coordinates of the point. Set-theoretic operations are different as they add or remove points from the object. They are also applied to two arguments, not to one as the above operations. For example, the union operation includes a point in the result if it belongs at least to one of the initial objects. Intersections select only common points of two objects. The difference includes points belonging to A and excludes points belonging to B. These operations are illustrated for two-dimensional and three-dimensional objects on the slide. In the course, we will consider different shape representations, such as boundary representation, constructive solid geometry, sweeping, voxels, volume modeling, and function representation. All these representations are based on different approaches to defining a point set. In the boundary representation, a solid is represented by segmenting its boundary into a finite number of bounded subsets, usually called faces or patches, and representing each face by its bounding edges and vertices. Historically, FRep evolved from a description of polyhedra in computer graphics. This description is based on the elements of polygons such as shown vertex, edge, and face on the triangle. The boundary representation is now dominating commercial CAD and animation systems. Let us consider an example, a boundary representation for a cube. A solid can be represented by its boundary surface. To define a boundary surface, one can introduce points, vertices, curves, edges, and surface patches, faces, and stitch them together. This boundary representation, or FRep, has two parts. Right part of the figure. Topological information on the connectivity of vertices, edges, and faces, and geometrical information, embedding these boundary elements in three-dimensional space. Topological information specifies incidences and adjacencies of boundary elements. Geometric information specifies coordinates of vertices or the equations of the surfaces containing the faces. See the solid object at the left. Its boundary representation is shown at the right. It consists of 9 faces. 2 of them have holes and 1 has curved surface. Even from this simple example, it is clear that it is not easy to build a FRep model manually. Next representation is constructive solid geometry, or abbreviated as CSG. It's one of the main representations of solids based on a set of three-dimensional solid primitives and regularized set-theoretic operations. This representation is based on implicit functions that play the role of primitives. Traditional primitives of a CSG system are block, cylinder, cone, sphere, and torus. Standard operations include union, intersection, difference, plus translation and rotation. A complex solid is represented with a binary tree, usually called CSG tree. Don't be surprised, please, these trees are growing with the root up and leaves down. A typical binary structure includes the root, purple color in this figure, nodes, pink-orange, and yellow leaves. In the case of the CSG tree, the root represents the resulting complex object. The nodes contain operations and leaves contain primitives. If a node represents a linear operations, such translation or rotation, such a node has only one child subtree, for example, operation number 4. All nodes with the set operations have two children, operation 1, 2, and 3. These are more complex CSG trees with the primitives and intermediate solids drawn in the nodes of the tree. Just 8 primitives make a quite complex model at the left. The next representation scheme is a sweeping representation, or simply sweeping. A set of all points visited by an object A moving along a trajectory B, see the top image, is a new solid, called a sweep. In translational sweeping or extrusion, two-dimensional area moves along a line orthogonal to the plane of the area. In this small animation, the non-regular area is moving along the axis X and sweeps a three-dimensional solid. Rotational sweeping is defined by rotating an area A about an axis B, left image. Here we also can see the animation. Now let's consider volume modeling with voxels and function representation. Spatial occupancy enumeration is a special case of cell decomposition with identical cells arranged in a fixed regular grid. The cells are often called voxels. The most common cell type is a cube, and the representation of space as a regular array of cubes is called a voxel array. We can see here a voxelized torus in the image as a typical example of this representation. For every cell, only its presence or absence in the grid is defined. A cell is presented in the grid if it's occupied by the object. The disadvantages of this representation are following. We always work with approximated model, and it's connected with a high memory consuming. Volumetric objects are extensions of spatial occupancy enumeration. Some numerical value is defined in the node of 3D grids. It can be density, temperature, pressure, and so on. Some volumetric objects can be defined from MRI scans using threshold of values, as you can see on this slide. Now let's look at the function representation. More formally, the function representation can be defined as a uniform representation of multidimensional objects defined by real continuous functions. The function value is calculated at any given point by evaluation procedure traversing the construction tree structure, with leaves containing primitives and nodes containing operations. One of the fundamental features is system extensibility, meaning that neither the set of primitives nor the set of operations are fixed and can be extended depending on the application area. This is an example of the construction tree using function representation. Let us characterize the function representation. It's closed under the arithmetic, set-theoretic, Cartesian product, projection, and other operations. It means that each operation yields a new real function describing its result. The abstraction level is higher than that other known representations, because combination of the following modeling styles are supported, such as CSG, sweeping, implicit, volumetric, and procedural objects. Here you can see different modeling approaches which are united by function representation. Function representation, or FRep, contains such unary operations as deformations, offsetting, projection, and sweeping. Here you can see an example of sweeping operation. The binary operations in FRep are following. It sets theoretic operations, blending, and metamorphosis. The special types of R functions are used for the set theoretic operations in function representation. Such functions allows you to get a smooth result of combining primitives without unwanted artifacts, as when using min-max operations. This is an example of the metamorphosis operation. You can see that the objects can have different topologies such as number of holes, and still this is handled automatically by the modeling system. But in the case of the other shape representations, for example polygonal meshes, it would crash without any acceptable result. Our course is related to additive manufacturing and 3D printing, so we will look at contouring and polygonization algorithms for slicing of function represented models. The second part of our course is called heterogeneous volume modeling. It's devoted to mathematical models for 3D volumetric modeling, multi-material modeling, and microstructures. This is a list of prerequisites for creating a unifying model for heterogeneous volume modeling. Modern manufacturing technologies require mathematical models and software tools for modeling internal structure with non-uniform distribution of material and other attributes, for physical simulation, geological and medical modeling, and so on. For description of the heterogeneous objects, let's introduce the constructive hypervolume model, which consists of the geometry described by FRep and attributes described by FRep2. The constructive hypervolume model has independent representations, but uniform treatment both for geometry and for attributes. Geometry and attributes are constructed using primitives based on the real-valued functions or scalar fields, and operations and relations. Here you can see an example of the hypervolume model construction. The left image shows the geometry, the right image shows the attribute space partitioning. By combining these two parts, we can obtain a complex heterogeneous object with a different distribution of materials or properties inside. This is another example of the heterogeneous object built using the constructive hypervolume model. In the next few slides, we provide a short list of earlier and modern CAD systems and kernels. This is FRep-based interactive modeling systems. CSG-based hybrid systems are presented on this slide. A list of FRep-based systems is presented on this slide. Of course, today there are many other commercial and open source CAD software. All materials for courses, including video lectures and practical tasks, are available on special web pages. Links can be found on this slide. Practical tasks consist of 7 computer-based laboratory works. The first 2 of them are devoted to the boundary representation on the plane. You will need to implement algorithms for drawing lines and primitives and using the geometric transformations on the plane to create an animation. An example of software application with source code, which you see on the slide, will be given. You can use your own preferred software development environment or use given C++ example. The next 2 laboratory works are devoted to the boundary representation in 3D space. You will need to build a 3D scene with a shape and a polygonal representation of that shape. The next 3 laboratory works are devoted to the heterogeneous volume modeling. These are volumetric modeling, microstructural and multi-material modeling. At the end of the course, you will get theoretical and practical experience in geometrical and heterogeneous modeling, as well as improve your programming and software development skills. Now I want to present you topics for master thesis provided by our research group. The first one is modeling of natural microstructures. Can you suppose what is natural and what is artificial microstructures on this slide? And this is the right answer. Here you can see a figure from a medical article. Authors studied structures of healthy and unhealthy parts of the bone. It takes a lot of time and money to do computer tomography or to slightly slice a dyed bone for performing geometrical reconstruction of such structures. It would be perfect to find some tool for good approximation this complex geometry, and we want you to help us with it. So, how can we do that? What do you think if the material distribution is random here, but looks quite noisy, isn't it? What about these structures? Are they random or not? Actually, all of them is called solid noises. These structures were obtained by FRep modeling, which you should remember from previous slides. The left shape has combination of trigonometric function in its formula. The middle and the left ones have pseudo-random components. The research group of Alexander Paсько already made an attempt to model organic-like porous structures. They did it using 3 steps shown on this slide. This research should answer many questions. The first steps of this research are presented on this slide. Name of the second topic is a moment vector approach to analysis and optimization. Let's discuss what this complicated phrase means. Suppose that you colleagues performed a good research on the first topic. What's next? Of course, we are interested in simulation with obtained structures. How can we do them? Here is the way we tried before. The first step, we convert a FRep model to STL file. The second step, import it to some solver and perform the analysis. But there is a problem. For example, we got such STL file for a quite small structure. You saw the accuracy of STL file for this model. It's 20 by 20 by 20 millimeters. It consists of 142,503 triangles, and its size is almost 27 megabytes. If we consider slightly bigger structure with the same pattern, we would obtain almost 4 times more triangles in 3 times larger file. Of course, it leads to significantly harder computations during the simulation. So, The moment vector approach is a mesh-free method for analysis. It does not depend on the topology of the considered geometry. It was applied to FRep, CSG, and voxel models. Our question is, can it be applied to function representation? Probably you can find more suitable mesh-free method for this purpose. And the last topic naturally appears from the previous ones. If we can analyze structures, it would be convenient to optimize their geometry in order to satisfy some objectives. For example, here is a statement for compliance minimization problem of an elastic body. We can try to solve this problem with two ways. The first one option is method based on usage of derivatives. For example, Newton-Raphson method allows us to find an extremum of a function with a second derivative. You can see how it works here. Do you know what is the problem of this method? If everything goes well, it brings us to local optimum. On the other hand, there are probabilistic methods which promise us to find a point that is close to the global optimum. The question here is, can we make a hybrid method out of these two approaches? And does it make any sense at all? Thank you for your attention.